Ahmed Kebaier from the University of Bermuda, who will talk about the dual approach for hedging Bermudan.
Thank you so much for the introduction, and thank you for this nice invitation, kind invitation in this nice conference. So the program for the next talk is not about signature, but about one, old question about a pure dual approach for hedging Bermudan option. So this is a joint work with Aurélien Alfonsi and Jérôme Leland, in which we're interested to go back to the setting of dual approach for pricing American option, because we got new ideas and we tried to explore them. So let me start with the setup. So the first ingredient for computing Bermudan option, so you need to have a discounted payoff process. So you can think that Zn is kind of discounted payoff process. It could be a call or or put or any discounted payoff process. So we are going to assume that time is discrete here, and we have some filtration, and we are going to assume that the running maximum of our payoff is LP integrable. So it's known from the American option theory and Bermudan option theory is that the discounted value of the Bermudan option is given by the supremum over all the stopping times here, tau, in this set from n to capital N of this expectation of this payoff. So of course, if your time here, the set time here, the stopping time value is reduced to one final date, which is capital N, of course, there is here, it's simply, of course, you got the price of an European option. But if you allow your, the owner of the option to exercise at different times, of course, then in order to price this kind of options, you need to compute this supremum over all the possible exercise times, right? So the owner of the option may exercise at any times in this set. So that this is the fair price that you should ask for such option. Of course, this is the discrete version of the American option, because the American option are known to give you the right to exercise at any time between 0 and capital T. So here we fix some time grid. So there are stopping times. So I'm going to assume that tau star n is the optimal stopping time. Okay, so the optimal stopping time maximizing this expectation. So if you know it, if you have this information, then you can simply run a Monte Carlo, right? You can run a Monte Carlo on this expectation and you got your American price. So from this theory is connected to the Snell envelope theory. And it's known that the solution of this problem is given by this dynamic programming algorithm. So you start from, maturity, time maturity, which is capital N, and of course, the price then of the option is simply the payoff. Okay, and then by backward, and using a backward angle algorithm, which is nonlinear, and this is the problem for American and Bermudan option, is that you have the nonlinearity here. So you have to compute the maximum between the current payoff and the previous, the conditional expectation. So you project the previous price of your option on your information today. Okay. So this is, of course, this maximum covers the two scenarios, which are the first scenario is at time k, the owner of the option is going to exercise. So the payoff is then ZK, and the second option is going to wait until the next time in stopping time in the time grid. So in that way, in order to be able to hedge correctly the next move, you need to hold kind of European option. So between two stopping times, it's behaving here like an European option. Okay. Alternatively, there is another way to formulate. So either you can stick to this setting of conditional expectation, or you move to the second one, and then you need here to run an alternative dynamic programming principle, but now on the stopping times. So on the stopping times, you start by default with the final one, which is equal to maturity, and then you update it, right? You update it whenever the payoff is larger than the conditional expectation or not. So if it is larger, then you update your, sorry, it's TK. So you keep the previous one or you update it. So this is the setting. So let me give you a brief review about the literature on this. So of course, to compute the problem in American and Bermudan option is the challenge comes from the maximum, the non-linearity, but also for the computation of the conditional expectation, which is generally done if you want to use Monte Carlo. So you use here linear regression, for example, for computing this conditional expectation. So the first approach, I mean, if you consider the first programming dynamic here, the dynamic programming principle here, the first one, this is done by Titikilis and Van Roy. They directly approximate on this dynamic programming problem. And later on, Longstaff and Schwartz provide a very famous popular algorithm in which they alternatively approximate the optimal stopping time tau star using the second dynamic programming problem I showed you right here. So what are the issues of this? So there are two main issues here. So the option price should be for the option seller the value of the hedging portfolio. Okay, so it should reflect somehow the price that the seller proposed should reflect somehow a possible hedging strategy, which is not the case here. I mean, for this, Longstaff Schwartz provides you a price. Of course, you can hedging this, especially in high dimension, is not possible. And these prices are pointless if we do not know how to build, of course, corresponding hedging portfolio. So starting from this, we got a look on the literature. What are the ways in covering or hedging, replicating these options? So one first paper appeared. This one is by Wong and Keflish, or Belomestny, Milstein, and Spokojny have proposed algorithms to compute degrees. Okay, so for one dimension, it's okay. But for higher dimension, it's not clear how you would find and select or find something matching in the financial instrument, tradable instrument on the market that matches your computations. So it could be from a theoretical point of view, it's okay, but from practical point of view, there is still a gap, which is missing here. So this is called, what I presented right now is called the primal methods. So now let's move to the dual formulation. So Rogers have two main papers, and there is another paper by Huff and Kogan, 2004, that reformulate the problem of pricing in American option in a dual approach. So if you remember the price here, the price essentially was this given by this supremum of over all the stopping times in this set, right, of this conditional expectation. So the idea here is to find an upper bound, right? So clearly the payoff here, when putting the maximum inside the expectation, is an upper bound of the American price. And you can adjust that using, for example, a martingale. Assume that your martingale here is, for example, Mn is equal to 0, starting the value is 0, and you adjust this expectation with the martingale, and then take the infimum of this martingale. It turns out if you do that, thanks to the Dubmayer decomposition, so if you have a Dubmayer decomposition, the Dubmayer decomposition gives you the M star here, and it turns out that for that M star here is the one that realizes the infimum here. And more than that, you can prove that UN is equal to the maximum here, the running maximum of the difference between the payoff and the optimal martingale. So in the literature, this M star is called almost surely optimal martingale. So this almost surely optimal martingale, of course, is theoretical. It's not, you cannot compute it, right? Because even, of course, there are attempts in order to approximate this M star, but there are still approximation. And if you have such an attempt, means that you have a pre-computation procedure before. So, so we started from this setting, and our aim is to find, is it possible to find a new formulation of this problem? And the interesting question, are we able to find a way to approach this M star without any somehow pre-computation step? Or at least in the smooth, finding a natural algorithm doing that? Yes.
Are you looking for
That's yes. So that's for the moment the M star from the Kebaier. But I'm going back to your question. There is a specific slide on that. I mean the uniqueness of this. So so the dual formulation. Let me give some comments here that may help later on, because our strategy is not only computation, the computation of the Bermudan price, but provide a hedging strategy, which is missing. I mean, up to our knowledge in the literature, at least for high dimension or sophisticated payoffs. So what we can notice that is that from the dual formulation, this V0 is a natural upper bound for the price, right? So if we choose a martingale on the market, think of the discounted asset price, right? This is tradable on the market. So if we start from this V0 plus MN, this can be interpreted as a self-financing portfolio, of course. So if it is self-financing, and as noticed by Rogers, if M star by chance is tradable on the market, then you have a perfect hedge in this case. So it means that this Z tau star is the payoff at the optimal exercise time that the client, the owner of the option, choose to exercise at that time, okay? And this is your portfolio. This is the price for the Bermudan option plus your strategy, okay? M tau star. And here we provide a very tiny observation here, is that if we now don't know the M star, and if I choose any other naive martingale, the error I'm making here between the optimal payoff here at the payoff at the optimal exercise time and my here hedging portfolio, the L2 error is the L2 error is controlled by the L2 error between your choice of martingale and the optimal martingale. So this is one first observation. So the dual problem is convex. That's good. But as Christian mentioned, this may admit many solutions. I'm going to give, more details on that. So this is another problem. And the problem here, as I told you, the motivating question is, are we able to approximate this M star and find a new dual approach or representation? So let me say a few words on existing algorithm based on the dual formulations. So there is a very famous, popular paper by Anderson and Brody that proposes to use the dual formula as a price here to give a price upper bound, okay? And they approximate M star here with the Longstaff-Vast algorithm first, and then use it in the second step in the dual formula. So they have a guess for M star and then plug it in and have the dual price. Rogers himself presented this different algorithm. He wanted to minimize this. Means that the space of martingale, he thinks that is linear, right? He's a linear space of martingales, right? And he tried to minimize this expectation. And of course, this only works if your choice of M0 is close to M star. Otherwise, this fails. So let me now move to the main result of this study and the corresponding algorithm. So the idea, as you can see, starts always from multi-level, telescoping sum, but written in a different way. So the main idea comes there from this. So this running maximum, you can write it in this way. You can write it as the final here at final time, right? Plus some telescoping running maximum. You can do that, okay? So this is the first step. And then you adjust using the Mn plus 1 here, same thing. And then simply using this property, the maximum between A and B minus B is simply the positive part of A minus B, you end up with this new representation. So, so this is just algebraic, representation of the running maximum. You can write it in different ways. So let me give some comments on this. Now take the expectation on this last formula. If you take the expectation, so this is the quantity of interest. We are able to split it in this way. So the blue term stands for the price of a European option, right? Because capital N is the maturity time, right? So means this expectation splits into price of an European option plus a sum of red terms. So this red terms, if you choose M equal to M star, they reduces to this positive part that we showed you before, right? But there, in this case, for any martingale, this is the given form, the associated form, right? So how you could interpret the red term? So the blue term is, as I said, is the price of an European option plus some extra reward that represents the gain if you exercise rather than continue. That's it. So you can imagine that the price of the Bermudan option is the price of the European option plus some corrections. And this is what where we started from. However, there are still here few challenges ahead, especially the positive function here, right? This is nonlinear and it's not strictly convex, right? So, and this is a problem in the optimization because you remember that from the dual representation, the price, you have to take infimum here, infimum on the martingale, and this is really a problem when you have the positive, function here, the positive part of this. So how to solve this? So let me introduce first the space of martingale increments between n-1 and n. So this is called HNP. So there are LP integrable random variable that are Fn measurable and with conditional expectation equal to 0. So as I said, it's tempting to now running the infimum, right? Running the infimum on each piece, because if you go back here, so this delta Mn plus 1 increment does not appear in this running maximum. Okay, it's a new term. So the idea is to say, am I able to run infimum on each new martingale increment? So it means instead of doing like Rogers and computing the infimum on the whole, from 0 to n, let me split the optimization problem in few ones, right? And each time optimizing the new increment. And of course, keep track the old optimized one. But however, as I told you, there are still theoretical challenging here, because you cannot you cannot stick to the whole path, of your previous choices because of this function is not strictly convex. So how to solve this? So as I said here, so it's tempting to running the infimum here and the new increment that does not, of course, appear in this running maximum. So the non-strict convexity of the positive part raises some issues in the backpropagation of the minimization problem. This is what the main message from this slide. And of course, going back to Christian's question, and even for this representation, there are many solutions. We can provide many solutions to the backward minimization problem. So this is, of course, not good for our framework. So here there is one paper by Schoenmakers, Zhang, and Huang. So if we use their approach, we are able to, of course, if we start from the Dubmayer representation of UN, and if I consider any sequence of random variable Zn, satisfying this assumption means it is positively, conditionally on Fn minus 1, it is almost surely positive, and the conditional expectation is 1, then this martingale Mn solves the backward problem. So it means that for any new choice of your Zn, you provide a solution, right? A solution for the optimization problem. And again, following the same setting, the paper by Schoenmakers, Zhang, and Huang, we can also, they provide a solution, of course, to avoid this. Their solution was based on holding a conditional variance penalization. I mean, this would guarantee the uniqueness, but the problem then is that this problem is no longer convex if you hold the penalization of squared term, right? Of course. So you lose the convexity here, and this is one main drawback of this approach. So we could, of course, do the same penalization here as done by Schoenmakers and co-authors, but here we decided to proceed in a different way. So we rather use this convexification. I don't know if the English word is correct, but I mean, it gives the correct sense. This is make the problem strictly convex. How? So this is the main theorem of the paper. It's the main result. This is what it says. It says the following. Consider a convex function phi that has a polynomial growth. So then what you can prove is that this expectation, right, plus the correcting sums we showed you before is always larger than the same quantity, but replacing M with the optimal martingale. Means that the optimal martingale is minimizing this, okay? And M star means that is a solution. If you take the infimum, means that M star is solution of this backward problem, minimization problem here. So M star is solution to this infimum here. Means that here I'm recalling again that the infimum is only computed on the new increments. Still, for each new increment, for n between 0 and capital N minus 1, I'm computing this running infimum. And the good news is the following. When phi is strictly convex, then also M star is the unique solution of this. Okay? So this is, if you take a few steps back and look to this, what says this results, means that I don't care about M star. I just need to change the function phi. It's not the positive function anymore. I take any strictly convex function. Think for the x square function, right? I'm solving this in a backward way on each increment, and I'm done. Because there is a unique solution. So the solution of the problem is exactly M star. So the proof is not sophisticated. It's just based on here. You apply Jensen inequality, right? Because phi is convex. And then you notice that you have equality only if this guy is Fn measurable, right? But this is satisfied by M star. And of course, the fact that it is strictly convex, this gives you the uniqueness of the problem. So this is the design of the algorithm. Then, as I told you, let us take, for example, P equal to, here P stands for the L2 space. So I have squared integrable random variable. And for each n between 1 and capital N, I choose a finite dimensional linear subspace of Hn2. And then backward, I'm going to minimize this sequence of optimizing problem on each here martingale increment. And this can be solved using any least square problem. I mean, any least square solver, you can use it, and it's okay. So at this step, there are two approximation errors here or needed here. The fact that, of course, we cannot we need a finite dimensional subspace. I cannot, of course, generate the whole space of HN2. And of course, the expectation here should be replaced by Monte Carlo sample, right? So there are two sources of errors. Okay. So let's move then to the finite dimensional subspace approximation. So then here, I'm thinking that for HNPR is using like Rogers' approach, that this is a linear combination of this delta xn. So delta xn are increments. I'm going to show you how you build this. And then the minimization problem here becomes you compute the infimum on alpha now, right? On alpha, so Zn plus alpha delta xn plus 1 minus this maximum. And you do it, of course, this is a sequence of optimization problem. And in each optimization problem, you optimize only on this variable. And the running maximum here is learned from your above, I mean, your previous steps. So of course, if you know that this guy is invertible, you can write an explicit solution for it, right? Because this is a simple linear regression or least square problem here. So now the second step is the Monte Carlo approximation. So you Q here, capital Q stands for the sample size, right? And then the idea then is to minimize, find the optimal alpha that minimizes this quantity square here error. And of course, you can write it in the same way, replacing the expectation by the empirical mean, and you find that alpha n plus 1q is solution to this linear system. Okay, so you can invert this or use any other solver, and you are done. You find your alpha. So we have also convergence results. What we proved is that the alpha nq here converges to the alpha n. So the alpha n are the ones for the problem with expectation, not with the Monte Carlo sample. And we showed that the price here, U0Q, which is the Monte Carlo approximation of this running maximum, converges almost surely to the expectation of the running maximum. And we do not have exactly central limit theorem, but at least we proved that square root Q of this difference is tight. So it means that the speed of convergence is Q. So if you know from the theory of American option, this is we faced the same problem, technical problem, as in the paper by Lamberton, Clément, and Protter, where of course they proved that the Longstaff-Schwarz algorithm converges to the price, and they proved not a central limit theorem. They just proved that the error is tight with the square root. Yes. Yes, here we were, I mean, yes, of course. This is, of course, reduces, of course, the set, but it looks, I mean, very tractable for practical needs. I mean, in the industry, what is really tradable is the delta xn. And what you can do with delta xn, if you want to keep the martingale property, is just a kind of linear transformation, right? Exactly. That's true. That's true. There in the numerical, maybe there are hints, maybe that will help you to maybe have a more appropriate answer. Thank you for the question. So so we have not a central limit theorem, but we are close to prove it. So it's simply that this error is tight. Okay. So let me go now to the financial framework. So for the financial framework, so let's assume that we are working on dia sets. So the advantage of this that we can allow ourselves to work on high dimensional setting, in a high dimensional setting. And here, for simplicity, we took interest rate constant. And then we assume that, of course, the discounted asset price is going to be martingale. So the time, exercise time for Bermudan option it's, I mean, we can assume them that they are come from a uniform grid. So this is not a big assumption here. I mean, it's not, it's a usual assumption. However, in what I said previously is that I don't need only to give a price for the Bermudan option, but I want to provide a hedging portfolio. So this is the using tradable assets. I mean, so here, of course, if you want to have a perfect hedge, it's known from the theory that you need to continuously, if you want to have a perfect hedge, you need to have a continuous time martingale, and you need to continuously rebalance, right, your portfolio in order to replicate the option. So in order to do that, we introduce, of course, we are still discrete in time, but we introduce kinds of subticks here, sub-intervals. So we refine, of course, there are some dates, new rebalancing dates between two exercise times of the Bermudan option. So this, of course, would help us to have a better, I mean, a better, we'll see, I mean, what happens clearly, I mean, from a practitioner point of view. And this is going back to the increment. So the things here is that we are going to assume that the increment, delta x, is a function here, a family function indexed by p. So p is between 1 and p bar. So this is a family function of the asset price, something tradable, the function you choose the function, right? Think of the delta, right? Think of the delta. This u is in one dimension, or Black-Scholes model is the delta, right? And this is a martingale increment here, okay? So what could be A? Keep in mind two examples. It could be the discounted asset price, or it could be any tradable option, right? That is a martingale, the price of any tradable option, yes. Yeah, it's a guess. Yes, it's a guess. I impose the U. I'm going to show you the typical examples. And essentially, yes.
That's kind of what I would optimize for U other than other.
Yes, you can do same thing, optimizing U other than. That's true. That's true. So, and now the alpha comes into play. So the martingale, the true martingale I'm going to use is this one. This is an increment of martingale. It's a sum of G and sum on all the parameters of P and Q, right? Of this constant, of course, of this increment. So the complexity of the problem is n bar times p bar times d bar. Okay, d bar is the dimension of your asset. I mean the assets that you are trying to hedge, or using for hedge. And typical choice. So joining the question. So the typical choice is indicator here, on some indicator function or polynomial function. You can choose a polynomial function if you think of regression or something like this. So let's move now 10 minutes perfect for the numerical experiments. Yes. Exactly. Even it may depend on the volatility, right? It could be richer than that. But our numerical simulation showed that even if we make them depend on the volatility, there is no real improvement. So it could be more than that, I agree. So let me go to the numerical experiments. So the usual, setting, Black-Scholes model. Let's keep things at a basic level. And here, so I'm interested in computing this U0, and then this, of course, approximates here this expectation when Q tends to infinity. However, we notice that Q, if you don't consider a large sample here, size of sample Q, then the number of parameters, and this is joins your question rule, the number of parameters is really larger compared to the Q. And this may create a kind of overfitting problem. So that's, and from this came the idea, the following idea. We start from a huge, very large Q, to avoid overfitting and approximate here the alpha IQ here, the coefficients. Once I have the coefficients, then I can move to a smaller sample, right? Because I learned here the alphas, then I can simply plug them here in the same problem, but with independent paths. Here, the red paths, the hat, Z hat, and delta X hat are independent from Z and delta X. So here you can allow yourself, of course, to run with a huge, large size of sample Q. And then here, once you learn it, okay, then for when you are ready to trade, you learn the alpha, then you can use for a smaller size of sample, and this is numerically is really efficient, as you will see. And we noticed that the difference here between the second approximation and the first one is always positive, right? And this is the measure of the accuracy tell us the following. If you have a small bias, of course, then there is no overfitting. Because here, I mean, we used new samples, right? We used new samples. So if the bias between the two approximations is small, means that you avoid overfitting. So a comparison with the Rogers approach. So with the Rogers approach, Rogers in his paper provides few examples in which he gives always a good guess for the martingale, which is always close to the optimal martingale. And the problem is this choice of martingale is really tailored for the chosen example. It's not, I mean, generic. And this is, I mean, the drawback. For example, let's take the case of a Bermudan put option. In this case, Rogers suggests to simply choose the price of the discounted as a martingale is the discounted price of European put option. That's it. And it worked really well, as you will see. Okay. So let me go and to the numerical results. So here is this table summarizes our numerical tests. So remember, Q is the Monte Carlo sample size here, and bar is the rebalance, how many rebalancing dates I'm going to put between two exercising times, optimal exercising time in the Bermudan time grid, and P is the size deciding of the family I showed you, UP. Okay. So this is the price, how it evolves. So from a very naive here approach, we got a price which is 9.91. By the way, Longstaff-Schwarz price is 9.99, and Rogers price is 9.94. So of course, if we allow ourselves to refine here, and allow ourselves to add, I mean, to use simply, so when I say vanilla is true, means that I'm including European options, price options. When I said it is false, I'm just, in my portfolio, just taking into account the discounted asset price. That's it, without adding other derivatives, okay? This is what it means. So we noticed that when we add, I mean, vanilla true, this is better. We got really close and better than expected. And if you forgot about vanilla, so vanilla, it's, when you add vanilla, it's like you are doing kind of delta gamma hedging, right? It's a delta gamma hedging. But if you avoid vanilla, you are still delta hedging. That's it, okay? So delta hedging, imagine you don't want really to do gamma hedging. You just stick yourself to do delta hedging. So you need to increase your rebalancing dates between each exercise time. And here you get close and close. But if you decide, of course, to use vanilla option in your hedging portfolio, you really are close to the Longstaff-Schwarz price. So, and this is the hedging error. So the hedging error, this is using only the discounted asset price. So this is the hedging error. And if you include, of course, vanilla options in your portfolio, you got better results. And we compared this to the Wong and Keflich, and we noticed that the skewness for Wong and Keflich is not the same one we got here using the delta. So it means that our approach looks more symmetric. I don't know. So now taking one challenging example, which is the butterfly option here. The butterfly, of course, use any guess you want. Even from Roger's paper, you will fail. So if you use here, for example, Roger paper, this is the price, 6.49 for this. I mean, take the European option price, discounted open option price with this payoff. This is what you obtain. Longstaff-Schwarz is 5.65. So there is a gap, right, between them. But if we use our approach here, including vanilla option, we are getting really close to the Longstaff-Schwarz, okay? And in an automatic way, I don't need really to find, it's really systematic method. And this is the hedging error, of course, when you include and you do not include the options. And now let's go higher in dimension, take dimension 2. Here, take a max call option. Same thing here. I mean, then it's the Longstaff-Schwarz here is 8.1. And here we notice it that we are getting close. If we increase Monte Carlo and if we allow to add vanilla options, we are really close to the true price. I mean, to the Longstaff-Schwarz price. So, and this is the hedging is perfect here. And when you include the vanilla, so you see you have a very tiny error. And the last example is a basket option on 3 assets. Also works well. So the Longstaff-Schwarz price is 4.03. And here we get really close in a systematic way. Of course, if I choose, don't need to tell you that if you choose the martingale, which is given by the European price, given by this is really far from the true price. So to conclude, the key ingredient here are the multi-level type telescoping sum to get this representation with rewards. And we got this new dual formula. And the second ingredient is this strictly convexifying the problem that allows us to approximate the M star from the Dumeyer I mean, the unique solution here in this case, with a bench of independent somehow optimizations going in a backward way. So this, the advantage is that, as you see here, there is the byproduct is that there is a hedging strategy that you can really implement in practice because we only used tradable asset price. Thank you for your attention.
We have time for one very short question.
Yes, we didn't include that. That's true. So I think we have to think even to start even from the model, right? We have in our Black-Scholes model, we have to take into account this friction. But what's a very nice question, because here what it says that from a trade, I mean, let me go to the first example, which is, I mean, a typical one. Sorry. Yes, this one. So this is what it says. It says that, of course, if you allow yourself to use vanilla, then you don't need to really refine too much. And maybe including transaction cost has no, exactly. So this is kind of a perfect hedge. But if you, such product is not available in the market, imagine this butterfly option and it's not, then you need to, gives you the idea how many rebalancing dates you should add in between each time step in the Bermudan grid, right? In order to reach a reasonable price, close competitive, right? Competitive price. So here, for example, you have to refine with a 20 intermediate date between each exercise time. So you can do your maths and okay, compute. But of course, we didn't take into account this in the model, the transaction costs. So this is still missing. But at least this numerical example gives you the idea how what is the real cost of doing that. If you allow yourself to to rebalance too much, a lot of, additional times in between two the exercise states. Thank you.
Very much.
Thank you.